Good day, I am Andrea May Anuevo, and today I'll be discussing absorption spectroscopy. So first, what exactly is absorption spectroscopy? Absorption spectroscopy, or AAS, is a single element method used for trace metal analysis of biological, metallurgical, pharmaceutical, and atmospheric samples. Spectroscopic determination of atomic species can only be performed on a gasified sample in which the individual atoms such as silver and aluminum are well separated from each other. So AAS is a very sensitive method of elemental analysis allowing for the determination of metals in a variety of samples at the picogram level. The absorption of light by atoms provides a powerful analytical tool for both quantitative and qualitative analysis. AAS is based upon the principle that three atoms in ground state can absorb light at a certain wavelength, and each individual atom has a specified wavelength it can absorb. It relies on the Beer-Lambert law, where it establishes the relationship between the sample concentration, which is needed in order to be analyzed, and the standards which come from known analysis. So, what exactly is Beer's law? So, this states the amount of energy absorbed or transmitted by a solution is proportional to the solution's molar absorptivity and the concentration of the solute. In simpler terms, a more concentrated solution absorbs more light than a more dilute solution. So here we have the formula of Beer's law, where the absorbance is equal to the logarithm of the incident intensity I sub O over the transmitted intensity I, or simply it is epsilon, or the molar absorptivity, multiplied by the length of the light path or the width of the cuvette, and C, the concentration of the solution of the sample. So here we have the process diagram for absorption spectroscopy. So the most common source for atomic absorption measurements is the hollow cathode lamp. As it says here, it consists of a tungsten anode and a cylindrical cathode, which is made of the element to be analyzed, and it is seated on a glass tube containing the inert gas, most commonly argon. Then for the sample again is gasified, so heat is needed to gasify the sample. The heat is generated from either a flame or a graphite furnace. So a flame atomizer consists of a nebulizer which converts the sample into an aerosol that is fed into the burner. The atomization takes place in the flame, commonly fed by the fuel gases acetylene and nitrous oxide. And then, after it is atomized and burned by the flame, a monochromator is used to isolate a narrow band of wavelength from the light spectrum, and a photomultiplier is used in order to convert these light signals into electrical signals, which are then detected by the detector and shown on the computer screen as results are to be interpreted. So there are two variations based on what instrument is used in order to gasify the sample. We have flame atomizers and electrothermal atomizers. So flame atomizers are the oldest and most common used atomizers in atomic absorption spectroscopy. These are commonly used to test liquid samples or solid samples which have been dissolved in a liquid. So using this process, a sample is first evaporated, and then they are vaporized and converted into gaseous molecules, which can be dissociated into free atoms. The atoms are then converted into gaseous ions, which can be exposed to a small flame. And during this process, the sample is exposed to a radiation beam, and the signal of absorbed electromagnetic radiation is measured as the absorbance. As for electrothermal atomizers, this is also referred to as graphite furnace atomizers, as they utilize a graphite tube to heat samples. So unlike flame atomization, which transforms the sample solution into an aerosol, this technique allows liquid, solid, and gaseous samples to be analyzed directly. So sometimes this delivers signals in a discontinuous mode. In contrast, flame atomizers deliver signals in a continuous fashion. Graphite furnace atomizers also minimize interference problems and can determine a wide variety of elements for most matrices. So as for the applications, AAS has been used for thousands of applications involving a wide diversity of samples, commonly in agriculture and forensics. For agriculture, one common use is for the analysis of soil samples and the effect that the quality of the soil will have on the overall rate of food production in a certain area. As for forensics, this technology has vastly improved the accuracy of toxicology reports in cases of metal poisoning because common causes of metal poisoning such as mercury and lead are easily detectable using this technology. So for specific examples, here we have a case study entitled Chlorine Isotope Determination via the Monitoring of the AICI Molecule by High-Resolution Pneumonia Source Graphite Furnace Molecular Absorption Spectroscopy. So this is a case study, and the atomic absorption spectroscopy instrument is used to investigate the possibility of obtaining isotopic information using, of course, AAS on the gaseous diatomic molecule generated specifically in a graphite furnace and a high resolution monochromator. So the results indicate that based on the addition of both palladium and aluminum, it enables the chlorine isotopic analysis with precision of values around 2% for solutions and chlorine contents at the parts per million level. So this basically just means that there is potential of isotope dilution for calibration, and it is proven that this approach can help in providing accurate results in situations where the occurrence of chemical interferences hamper the use of other calibration approaches. So, as for another application, here we have a research article entitled Quantitative Determination of Arsenic in Bottled Drinking Water Using Atomic Absorption Spectroscopy. So the total arsenic was determined in samples from 6 different types of commercially available bottled drinking water, and using AAS, the total amount of arsenic was determined. So as for the results, the method was linear with a studied range of about 1 to 5 micrograms, and the quantification limits for arsenic determination were 0.48 micrograms per liter and 0.03 micrograms per liter. So the evaluated arsenic content in drinking water was the accepted limits provided by the law. So in addition, a simple and sensitive method for the quantification of arsenic in drinking water was described and can be further used in other toxicology studies. Lastly, another application from a research article here with the title A Comparison of Blood Lead Level in Opium-Dependent Addicts with a Healthy Control Group Using Graphite Furnace Atomic Absorption Spectroscopy, followed by chemometric analysis. Here, AAS was used in the comparison of inhaled opium addicts with a healthy control group, using the graphite furnace atomic absorption spectroscopy followed by chemometric analysis. Sub to low microgram per liter concentrations of blood levels were detected in both addict and control groups. For the results, the mean concentration of lead was found to be significantly lower in the control group compared to addicts. Thus, it was observed that the blood lead level in opium addicts was significantly higher than that of healthy control group, as backed up by statistically significant results in statistical analysis. So that's all for absorption spectroscopy. Thank you for listening.